Now, a basis for the initial topology on the set X consists of all finite intersections of elements in the subbasis script S, which is the union of the inverse images under the maps f sub I of the topologies tau sub I, the open sets in the space X, therefore consist of unions of finite intersections of the elements in the subbasis script S. So as a third exercise, let tau sub script S be the initial topology on the set X. Prove that this topology is the coarsest topology on the set X, relative to which the function f sub I mapping x into y sub I is continuous for every index I. In other words, assume that there exists a topology mu on the set X for which each of the maps f sub I are continuous, and prove that the initial topology is contained in that topology. Okay, so new definition. Let x sub 1 through x sub n be sets. Then their product set is the set that is denoted with a capital pi for I equals 1 to n of x sub I. And this is Cartesian product of the set x sub 1 with the sets through x sub n. And this is the set of all ordered n tuples where the element x sub I is in the set x sub I. That is, the product set consists of all ordered n tuples, which I will denote with a vector notation, where the ith coordinate of the ordered n tuple is an element in the set x sub I. So let's look at an example Let x be the Cartesian product of the integers with the rationals and the reals. The elements in this set are ordered triples, which I'll denote x, y, and z, where the first coordinate, or x coordinate, is an integer. The second coordinate, or y coordinate, is a rational number. And the third coordinate, or z coordinate, is a real number. Okay, so new definition. Let x be the product set of n sets. The ith projection map is the function, which we denote lowercase pi sub I, mapping the product set into the set x sub I, defined by pi sub I of the ordered n tuple is the coordinate x sub I. That is, the projection map pi sub I maps an ordered n tuple to its ith coordinate, so new definition. Let the collection of sets x sub I together with a topology tau sub I for I in the indexing set of positive integers from 1 to n be a collection, or a finite collection, of topological spaces the product topology on the product set is the initial topology on the product set generated by the finite collection of topological spaces and the corresponding projection maps Now, the product topology on a product set has as a subbasis the collection script S, which is the union of the inverse images under the projection map pi sub I of the topology tau sub I, and this is the set of all inverse images under the projection map pi sub I of the sets U, where U is in the topology tau sub I, and I is an index in the set, finite set from 1 to n. Where the inverse image under the map pi sub I of the set U is the Cartesian product of x sub 1 and so on through the set U and so on through the set x sub n. That is the Cartesian product of the product set from j equals 1 to I minus 1 of the sets x sub I with the set U cross the product set from the index j equals I plus 1 to n of the sets x sub I. That is, the inverse image under the projection map pi sub I of the set U is a subset of the product set where for each ordered n-tuple in the set, the ith coordinate is restricted to elements in the set U, which is a subset of the set x sub I. And so we can think of the inverse image under the map pi sub I of the set U to be the intersection of the inverse image under the map pi sub j equals I of the set U with the inverse image under the map pi sub j not equal to I of the entire set x sub I, or correction, x sub j. So let's look at an example. So let x, together with some topology tau sub x, and y, together with some topology tau sub y, be topological spaces. The product topology on the product set x cross y is the topology generated by the collection script B, consisting of products U cross V, where U is open in X and V is open in Y. So proof: a sub-basis for the product topology on the product set x cross y is the collection script S, which is the union of the set of all inverse images under the projection map pi sub 1 of the sets U, where U is open in X, with the set of all inverse images under the projection map pi sub 2 of the set V, where V is open in Y. This is the union of the set of all products U cross Y, where U is open in X, with the set of all products X cross V, where V is open in Y. Notice that for every product U cross V in the collection script B, U cross V is the intersection of the inverse image under the map pi sub 1 of the set U with the inverse image under the map pi sub 2 of the set V. That is, every product U cross V in the collection script B is a finite intersection of elements in the subbasis script S, and therefore the collection script B is a basis for the product topology on the product set X cross Y, and hence the product topology is generated by this basis. So let's look at a more concrete example. So let R be the real line a basis for the product topology on R squared, which is the Cartesian product of the real line with itself, consists of all products U sub 1 cross U sub 2, where U sub 1 and U sub 2 are open intervals in the real line, so given an open interval, which we'll call U sub 1, and an open interval, which we'll call U sub 2, the inverse image under the projection map pi sub 1 of the open interval U sub 1 consists of all the elements in the subspace of the plane, where the first coordinate is restricted to elements in the set U sub 1, and the inverse image under the projection map pi sub 2 of the open interval U sub 2 is a subset of the plane consisting of those elements where the second coordinate is restricted to elements in the set U sub 2, and the intersection of these inverse images is the set u sub 1 cross u sub 2. So notice that the product u sub 1 cross u sub 2 is the intersection of the inverse image under the projection map pi sub 1 of the set u sub 1 with the inverse image under the projection map pi sub 2 of the set u sub 2.